Hi, Rashid here. So today in this video, we're going to look into a third stage of. So we are looking into different stages of synthesis with a very simple skeleton flow. And what we're doing is we are reading in a full adder, it's a very log file. So the fourth stage, actually, sorry, this video is about the fourth stage, which is applying constraints. So far we did setup, we did RTL, we did elaboration, and at this stage we have a GTAG database, which is independent of the process node. Okay, now we have, now tool has created a graph in the memory. It knows where the gates are, where the wire delays are, what kind of gates are those, and all that. Now it needs to eventually convert into the standard cell based netlist, and it need to optimize. And in order to optimize, in order to convert things, it needs some constraints. Tool needs some constraints. So the constraints required are timing. So a lot of constraints you can apply within each area, but on just the higher level. Okay, the timing related constraints, power related constraints, and area related constraints. Again, I'm going to do separate ones. So after going through the stage, I will do the first one on a standard cell library, what is the formula and all that. There will be a quick video on Tickle as well, or Synopsys Tickle, because I'm using Synopsys tools as an example. Then I will get into details of constraints, the timing constraint. But for now, I put some examples, so I think that's a good way to start. So the basic timing constraint is your clock, because we time everything with respect to clock edges. So the time between two positive edges, time between positive and negative, or rising or fall edge, and all that, that is a very important constraint. Okay. In our design right now, the system verilog file that we did, there is no flip-flop. But what I'll do is I'll put a flip-flop input, but right now there is no constraint. So timing, a clock is not there. So even if you provide a clock, this doesn't exist. In this type of design where you don't have flops, you can apply different timing constraint. You can set, okay, how much delay you expect from inputs to all outputs, or how much delay do you expect when the input comes and when output be stable. I mean, you need to give it some realistic delay. You cannot say zero delay, because it's not going to be a zero delay, right? So anyway, generally there are clocks. Every design, sequential design have clocks. So you can create a clock and tickle like this. Create clock, keyword, dash name, keyword, clock. This is the name you want to give it. Period. Here's the period you gave. I just put one, whatever time unit. And then on which pin, on which port you want to apply this clock, and we say there's a clock coming in, if this exists. Here's another one, input delays. Input delay is the external delays, and the signal that are coming into your chip or coming into your design, they're getting some delay outside, and it eventually be consumed inside. So in the timing constraints, you want to understand how much delay they have outside. Again, this I will cover what input delay means, what output delay is, but just here, you can apply some data. There are so many other constraints, type of constraints you can apply, and they have different keywords and syntax and all this. But cool, the thing is, you need to create a tickle file which provides timing constraints like this. And here's a good example of the Synopsys tickle. So when you provide all inputs, this is a command, and you put square brackets means it's going to be executed. And this is not a simple tickle thing. This is Synopsys tickle. It will bring you all the input ports in your design, and input delay of 100 is applied on each one of them. That's what this thing does. But we will look into timing constraints. Similarly, an output. This is an output port, and they will experience an output. Why you have to apply this and that, we can look into separately. You can apply a number of constraints. And generally is, okay, you can mention a maximum area in square microns that you want to keep for your design. You can mention that, and we'll try to follow that. You can also mention a lot of information, a lot of different things. For example, location of your ports, area or the dimension of your overall area. You can also provide some placement blockages. You can provide what metals and all that. You can provide a lot of floor plan information. You can provide just this and nothing else, or you can provide a lot of floor plan information. You will see that, and maybe it's a separate topic, that gate level synthesis has become more of a physical aware gate level synthesis. And even at the time of gate level synthesis, the modern tool Design Compiler, or I should say Fusion Compiler, or similar tool from other vendors, they have the capability that even at synthesis level, tool can see your floor plan and different constraints with it. And when it generates an optimal netlist, it can optimize is in such a way that given the dimension of the block, given the location of the pins and type of metal used, it can really optimize the design. And that is super good. At such an early stage as like synthesis, tool can do optimization with kind of close to final type of floor plan. Because of floor plan, it has to play this. These two ports are pretty far apart, so then it can optimize them better. So it kind of reduces the burden for the later stages coming in. Your starting point, a gate level netlist, is a starting point for your physical design implementation. And if your starting point is good, the following stages will do even better. And if your starting is a low quality netlist, then your following stages need to do a lot of work, and you will see a bigger miscorrelation between your QR reports in the later part of the design to earlier part of design. So a continuous push in the industry, and that's what I use recently, or most of the people use this, as opposed to instead of creating a simple netlist, non-physical aware, you really like to use as much physical information as possible at the early stage of synthesis. And we will look into pros and cons of that approach. But the bottom line for this video is you can provide some constraints here. Then power constraints. Okay, you can mention some target for leakage and all that, but I put here a UPF file. If your design has a single power domain or multiple power domains, each domain works on certain hierarchy, certain number of cells. Certain cells belong to 1.1 volt, other cells belong to 0.7 volts, certain will be off and certain will be on, and there are so many things related to UPF. So there will be a couple of videos on UPF in order to give you a basic format of UPF and how synthesis tool use that to come up with some of the additional things in the netlist. But for this video, you need to provide timing constraints, you need to provide area constraints, and you need to provide power constraints. And once you use those constraints and everything is good syntax wise and all that, then it goes into conversion into final netlist and a lot of optimization. Let's stop this video here. This is a lengthy topic and it's fine, I don't want to rush it. But I hope you got the concept of why we apply constraints and at what stage we apply constraints. All right, see you in the next video. Bye.